Hello guys, in today's video we're gonna solve this exercise which consists in finding critical points of this function here. So in order to find critical points that can be maximum or minimum or saddle point, we need to find the first derivative and put the first derivative equal to 0, right? So we would need to find the first derivative with respect to x and then with respect to y, right? So let's start by finding fx, which is the first derivative of this function with respect to x. So 3y is going to be a constant, then we're going to differentiate with respect to x. So derivative of x squared with respect to x is equal to 2x. Then we have here minus 3x squared, which is going to be minus 3, and the 2 comes down, so minus 6x, right? This implies that fx is equal to 6xy minus 6x, right? Now we find the first derivative of the function with respect to y. So this is going to be, here we have 3x squared, which is going to be a constant, so 3x squared, and the derivative of y is equal to 1, right? Now we have y cubed, so derivative of y cubed is 3y squared, and then we have here minus 3y squared, so the 2 comes down, so we have minus 6y, right? We have the two derivatives, so we're gonna put first fx is equal to 0 and then fy is equal to 0, right? Let's start by fx is equal to 0, which means that 6xy, which is here, a minus 6x is equal to 0, right? This implies now we have 6x on both terms, so we're gonna factor out 6x, and then we're gonna be left with y minus 1, right, is equal to 0. Now this implies that x is equal to 0 from this one, and we have y is equal to y minus 1 is equal to 0, which means y is equal to 1, right? We have our fx is equal to 0. Now we put fy is equal to 0, which means fy is here, so we're gonna have 3x squared plus 3y squared minus 6y is equal to 0, right? We can divide all by 3 because as you can see here we have 3, 3, 6. If we divide both by 3, we're gonna have x squared plus y squared minus 2y is equal to 0, right? Now it's much simpler. As you can see from the first one, we have x is equal to 0, y is equal to 1. We can say when x is equal to 0, we substitute it in this equation here, right? So when x is equal to 0, we're gonna have the y squared minus 2y is equal to 0, because if you substitute the 0 here, this is gonna disappear and we're gonna be left with y squared minus 2y equal to 0. This is when x is equal to 0, right? This implies if we factor, because we have y on both terms, so if we factor out y, we're gonna have y minus 2 is equal to 0, and this implies that y is equal to 0 and y minus 2 is equal to 0, right? And y minus 2 is equal to 0 implies that y is equal to 2, because we bring the minus 2 on the right hand side. So when x is equal to 0, we have that y is equal to 0 and y is equal to 2. So here we have two critical points, right? So when x is equal to 0, we have y is equal to 0, and when x is equal to 0, we have y is equal to 2. So we have two critical points here, and these have just two coordinates, x and y coordinates. So later on, if we want to find the exact point, we need to plug this into our function to find the z coordinate, right? But for now, let's just consider the two coordinates x and y. So we can define this to be our point 1, and this is our point 2, and these are the two critical points. Now, from the first derivative, we also had that y is equal to 1, right? So now we say when y is equal to 1, and then we're gonna substitute in our equation here. We're gonna have x squared plus 1 minus 2, because 2 times 1 is 2, is equal to 0. This implies that x squared is equal to 1, because we bring all on the right hand side, and this implies that x is equal to, let's write it this way, x is equal to 1 and x is equal to minus 1, right? So when y is equal to 1, we have x is equal to 1, x is equal to minus 1. So we can write other two critical points. So when x is equal to 1, y is equal to 1, and x is equal to minus 1 and y is equal to 1, right? We have other two critical points, so let's call it P3 and P4. Now that we have the critical points, in order to find whether they are maximum or minimum or saddle point, we need to find the second derivative, right? Let's copy the first derivative that we found. We found before that the first derivative with respect to x is equal to this. Let's paste it here. And the first derivative with respect to y, let's copy, was this, right? Now we need to find second derivatives, and then we need to do something that we're gonna see later. So second derivative, we find the second derivative with respect to x. So let's first find fxx, right? Fxx is equal to the derivative of this with respect to x, right? So if we do that, here we're gonna be left with 6y, because 6y is gonna be a constant, minus 6, because this is we have here x, so derivative of 6x with respect to x is equal to 6, right? Now fxy, so the derivative of this with respect to y, yeah, so derivative of this with respect to y. By the way, this is the same as fyx, because the function is continuous. Just with respect to y is going to be just 6x, right? Because here with respect to y, so 6x is going to be the constant, and then the derivative with respect to y is going to be 1. Now we need to find we have fxx, fxy, fyx. We need to find fyy, right? Fyy is the derivative of this with respect to y, right? So this is gonna be 0, this is gonna be 6y, and this is gonna be minus 6. So we have 6y minus 6. So now we have all of them. Now what we're gonna do, we're gonna define d to be fxx times fyy all minus this square. So d is defined to be fxx times fyy minus fxy square. So in our case, d is going to be equal to fxx, which is, as you can see, fxx is the same as fyy, so we just gonna square it, right? And then we gonna subtract the 6x square, right? This implies that d is equal to 36y square plus 36 minus 72y, and then minus 6x squared is going to be 36x squared, right? So we have our d. Let's just write it properly. I'm gonna put this down here. So this implies that our d is equal to this minus 72y minus 36x squared, right? Now what we're gonna do, we're gonna plug the critical points that we found, which are four of them. Let's copy them down here. Copy and paste it here. Let's copy this one and paste it here. So we have these 4 critical points. Now we're gonna plug these critical points into this d, and then if we find that d is less than 0, then we can conclude that we have a saddle point. If instead we find that d is greater than 0, then we need to see whether the fxx is greater than 0. If it is greater than 0, we conclude that we have a minimum point of relative minimum. Let's first plug this 0, 0. So we're gonna have the, let's write it as d0, 0. So we plug this point 0, 0. It's gonna be equal to, this is gonna be 0, this is gonna be 0, this is gonna be 0. So d0, 0 is equal to 36, right? And 36 is greater than 0, right? So our d in this case is greater than 0. Now we need to see whether fxx is equal to, is positive or negative, right? So fxx, let's say 0, 0 here, 6y minus x. So if we plug 0 here, this is going to disappear and we're going to be left with minus 6. So fxx 0, 0 is equal to minus 6, which is less than 0. So we can conclude that this point p1, 0, 0. I've left this space here because then we need to find the z value of this point, right? So p1, 0, 0. So this point is the local maximum. This first point here is a local maximum. Now we need to do the same for all the points, critical points we have. So now the second point was 0, 2. So d0, 2 is equal to, if we substitute to our d here, d0, 2 is going to be 36 times 2 squared, which is 4, plus 36 minus 72 times 2, right? To 36. This is going to be equal to 36 because this and this, they're going to cancel out, and then we're going to be left with 36. So in this case, d is also greater than 0. So then we need to look at fxx of, in this case, 0, 2, right? We need to plug 0, 2 in our fxx. So if we plug 0 to here, so we're gonna have 6 times 2, which is 12, minus 6, which is 6. In this case, fxx02 is 6, which is greater than 0. We have instead here a local minimum because fxx is greater than 0, right? So we say that our point 02, this point is a local minimum, right? So our point P2, which is 02, is a local minimum, right? The second point is a local minimum. Now we need to do the same for the third point, right, which is 1 1, right? So we have D11 is gonna be substituting 1 1 in our D. So we substitute 1 1 in our D. So we're gonna have that D11 is equal to 36. Where is the 36 plus 36 minus 72 minus 36, right? So 36 plus 36 minus 72 minus 36. So D11 is going to be equal to 36 minus 72, which is minus 36, which is less than 0, right? So here our D is less than 0. We can conclude that the point is a saddle point, right? So P3, the third point, which is 1 1, is a saddle point, right? This is the third point. Now we need to find the last point, which is this one, P4 minus 1 1. So let's do the same. D of minus 1 1, the D is here, so we're gonna substitute minus 1 1 in this here. This is gonna be 36 plus 36 minus 72 minus 36, right? So D minus 1 1 is gonna be 36 plus 36 minus 72 minus 36, right? So this and this, they cancel out, so we have 36 minus 72, which is minus 36, which is still negative, right? So D is also negative in this point, so we have a saddle point here as well. So P4, which is minus 1 1, is also a saddle point. This is also a saddle point. Now we have all our 4 critical points, and we can draw our graph. If we want, we can plot the graph. We can plot it using a software called Maple, and then we can also find the z coordinate of each point. So let's do that. Let's open Maple in TeamViewer. Right.